All right, here we go. Final speaker of the night before the door prizes. And then, of course, more importantly, drinking and video games. Without further ado, though, this is one of my personal friends, Mark, and he's going to give a great talk on the chemistry of cyber physical attacks. Please give a good round of applause for Mark, everybody.
All right. Thank you, everybody. Hopefully we won't make this too long. We know it's coming to the end of the day here. But we're going to take a little bit of different direction on this one, which is I want everybody to start thinking about different types of attacks and attacks that are a little less common than what you're used to. So one of the things that we specialize in is where cyber meets the physical world. It's definitely the devices and things. A lot of what we do is critical infrastructure and that sort of thing. So a lot of those things are where you have pumps or valves or those types of things. And obviously a cyber attack to that sort of stuff can have real world consequences. And that's part of what I want to go over today. Let's see if I get, yep, so much for that. All right, before we get too far, I just want to get a couple disclosures here since I'm going to go over a bunch of stuff. One is I am not a chemist. So despite talking about some of this chemistry, do not think I am a master of chemistry. I just have enough to be a little dangerous. I'm also not an engineer. In fact, I'm not really a particular expert at anything. More of a jack of all trades, but I do work in a lot of industries that, work in these different areas. I'm also not a professional researcher, so the information does not mean I did necessarily a scientific model to come up with it. The examples are anything you can find publicly. While I did tap into a lot of personal experiences and seeing some of these things in the environment, many of these may still be hypothetical, and sometimes I'll even relate to something that wasn't really necessarily a cyber attack, just as an example. One of the other things is everyone here, if you do have a question, we don't have to wait to the end, or if you want a statement or add something to it, just stand up and shout it. I'm pretty informal about this sort of thing. So first of all, is just finding out if anyone here did this stuff today. Did anybody take a bath or a shower? There's a lot of people who are not raising their hands. I would, spread out a little bit farther. How about to have a drink of water? Anybody drink water today? Good for you guys. Way to drink some water. Consume a prepackaged food or beverage. Oh, a bunch of people did that. Maybe some more than water. I don't have to worry about that. Riding a vehicle. Anybody riding a vehicle all day? Got a bunch of those. Oop. Let's see here. Turn on a light. You did the hard stuff. And how about take any medication? Got a few people taking medication. All right, well, we'll get a couple of things here, and I'll explain what all that has to do with this. Chemistry is the science that deals with the properties, composition, and structure of substances, defined as elements and compounds, the transformations they undergo, and the energy that is released or absorbed during these processes. That's just to give us a nice working thing about chemistry, and also how it's going to relate to cyber. In critical infrastructure, you'll see there's all these different sectors that are kind of recognized. And one of the things about that is we conducted a course, and in that course, we asked people to think of all the different types of things that can be affected in each one of those by various things, whether affecting digital assets and also any type of chemistry involved in that. As you can see, there's quite a bit across that. Had the biggest trouble with, seemed like most people had the biggest problem with financial services. So before I get into this, all of those things obviously we talked about have something to do with chemistry. They're something that can be affected, and a lot of people don't think much about that, and they certainly don't think about it much in the way of cyber. And that's one of the ways we wanted to talk about that. I don't know if anyone remembers, but there was a hack Oldsmar hack in Florida just a couple years ago, and that was very telling. In that hack, there's a few things that we know. Sodium hydroxide, this is a kind of key thing here. It's supposed to be 100 parts per million, and the hacker set it to 11,100 parts per million. Now that's interesting because for those of us who know anything about the water stuff, you can very easily tell that they weren't necessarily trying to do something evil intent. It was more playing around. They just simply added some ones to the value, and that's what got that going. If you were a little more sophisticated, they could have done a lot more harm and damage than what was actually performed. They accessed it using TeamViewer. I don't know how many people are familiar with that, but we'll certainly talk about that. There's speculation that the 4-digit permanent password was used or it was disabled, and we'll get to why. It's a Windows 7 that was completely unpatched, which is, by the way, not uncommon in most of these industries. There was 24 to 36 hours prior to water being distributed. So what that tells us is they had a little time on this, which is after something went bad, they still had a day or two before that water would make it out to the public, and that's why they could stop it. They did have plenty of redundancies. That's not uncommon in these things. A lot of those redundancies are having additional alarms or manual actions in order to check them. So what's the concerns? Well, it's often unknown whether all those redundancies are or are not digital. So a sophisticated attacker would not necessarily just attack one component, but would have the capability to go after more than one component. That being the case, obviously things like Stuxnet, in which case you can make a sophisticated enough attack that takes out multiple pieces of equipment or even gives you a pathway to it. That's a perfect example of that. It's, their inability to determine the origination of the attacker. That just shows that there's such a lack of cybersecurity at the time that they couldn't really monitor or know where it came from or why. It was very limited information. And then overall, like I said before, it was pretty much an example of amateur hour. The hacker was more experimenting and figuring out what the system was and what they should do rather than actually had a plan of attack that they were actually trying to implement. So, TeamViewer, for those who don't know, is a proprietary piece of software. It's just a way to remotely control a computer. It's not all that sophisticated. But what does TeamViewer actually say about this? If you were doing the docs at the time, right in the middle of the docs, it actually talks about how it can be irritating to have a password. So right in there, they go and they give you a variety. I know this is very hard to see, but a whole bunch of settings. The default is a four digits. And when I say digits, it's basically numbers. And since by default, this is just software runs on a PC, you could just bang against it until the end of time until it lets you in. But it gets worse than that. Because it's irritating, they give you an option to just disable it altogether. So, which is often, I hate to say it, done. So, it was hardly the first or the last. There's been several attacks, but all very one. The big notion of that one is that it actually affected something physical. Dumping chemicals or the ratios of chemicals in the water. You have other ones which they've been playing with, certainly spear phishing attacks, and you have all kinds of different attacks going after various components, but most often it's ransomware. Obviously, that's the money maker at the moment. Was an undisclosed ICS attack with water sewage, and it occurred over a 2-month period. You had another one that the SCADA system was hacked. For those who don't know, SCADA is, used pretty heavily in industrial applications. And then you had, like in 2013, a SCADA system in New York, which they know was, or fully suspect was hacked by Iranian operatives. So that means, you're talking about 4 nation-state attempts that can do this stuff. And it's pretty new still, despite being in industrial, us all being aware of it. Those attacks certainly exist, and that means they're watching us. So I wanted to show you a little thing here showing the change in perspective. In 2015, the FBI stated basically that they just advised people to pay the ransom. Now, you come to 2021, and they don't support paying ransom. So, lesson learned, I guess, that paying the ransom didn't stop the activities. We're in fact seeing more of them. So here's some more examples of this stuff, just publicly out there. A perfect one, which they're celebrating by even putting in the press, that they have, the Water Authority installed a bunch of remote wireless devices so that they could make their job easier. So instead of previously having to go out and reading the meters, they can now sit at home or at their desk and read the values. I want you to take note, if you can see it, what this picture looks like here. Just kind of remember that for a second. So here's the things that they say. It's, they can look at remote wells and pump stations. So these things aren't idle. They actually do stuff. Way down here, you see that they monitor chlorine levels. I know it's a little hard to see. And then over here, you'll see all these wonderful features they're proud about. Ethernet to IP, Modbus is another wonderful technology often used in the industrial stuff. And so they're going back and forth between IP, Modbus, and TCP so that you can make any hacker's dream come true. And then down there, they're nice enough to tell us the very exact model number of the device that they used in order to help with breaking into that. So, what do you have to do? Well, eBay's our friend. This is no longer the case where you have to spend hundreds of thousands of dollars to reproduce these things. Some of these things used to be really expensive, and that was itself a roadblock to hackers. Now you go on eBay, you can buy this stuff used for $100, $200. You play with it all you want. So, let's see. This is the software that runs on that PLC. You can download it from the web. You don't even have to register. You just get the latest firmware. It has the exact software that you use, and you can use that to reprogram any one of those PLCs. And as you see here, it's very simple. Has built-in ladder logic. It compiles it for you. So you don't have to do anything really sophisticated if you want to change that device. So this is not a one-to-one comparison, but just so you know, this is my pool. And I did something similar to this, which is obviously a little less than professional, but I made my own system to monitor the chemistry of the water in the pool. And as you can see here, these are the types of things that it monitors. And this is very similar to what they do. You have two kinds of things in a water treatment plant. If you're unfamiliar with it, you'll see this value, which is ORP. That's a rough way of determining whether or not that water would be safe to drink. And you can see in my particular pool, it plummeting. This number should be at least 600. So at that particular time, when I was messing with the chemicals to see what I could do, if you drank my pool water, it's probably not a good day. So, and as you can see, monitor everything, the temperature, and then here's the pH. This is me messing with the pH. Now, this is, of course, what saved that water plant, being able to see that the chemicals had an effect, allowed them to say something was wrong. However, if this is digital, like it is in my case and it is in many places, you could obviously make that graph say anything you wanted. So if I make that lie to the operators, it's much more likely that that would go through to the actual water supply. So let's talk about a completely different industry, nuclear. It's one I'm pretty familiar with. There's a lot of chemistry involved in the nuclear industry. Some examples of that, of course, water, same thing. They're very, very particular about their water also. Gases, they deal with hydrogen, oxygen, nitrogen, a whole bunch of other ones. You don't want things like too much hydrogen buildup, that sort of thing. So there's a bunch of chemistry involved to make sure everything's operating the way it should. They have a whole bunch of instrumentation which the operators use, not unlike the water treatment plant, in order to make sure that all of this is running and the chemistry is operating as expected. So you have a bunch of sensors, and lastly, you have the fuel itself, making sure that the uranium is the way you want it. So what are concerns about that? Well, the primary defense to all of that is redundancy. And believe me, nothing has more redundancy than nuclear power plants in the United States. For every system, there's another system, and for every one of those, there's another system backing that up. But that doesn't mean it's that not all of that is digital. In some cases, they have multiple digital systems. Analog devices are being replaced with digital. So one of the fortunate things that have happened over the last few decades is a lot of the equipment, the safety systems in particular, rely a lot on analog just because that's the thing when it was out. But it is literally becoming impossible for them to replace it with analog systems anymore. It's just no one makes them. It costs too much to manufacture them, so they end up replacing them with digital systems. The chemistry is not even considered a safety concern. So even though the chemistry aspect can have a deleterious effect on the on how a nuclear power plant operates or how it does it, it by itself is not considered safety because there's all these other devices that are used to monitor the state of the actual nuclear power plant. So here's some nuclear cyber incidents heavily involved in a few of these. The virus in 2003 blocked operator access to reactor core information. One thing to understand is that virus was not targeted or had nothing to do with nuclear. It just happened to be regular malware that ended up getting on a plant computer system. The Stuxnet virus, most people have heard of that in our field, but it is noteworthy, especially because, later there's been many variants based on the original Stuxnet code. 2011, there's many network intrusions in Ariva, which is one of the main nuclear, or used to be a main nuclear support customer. And one of the things about that is obviously they're looking for information about nuclear technologies and power plants. The Department of Energy, and NRC were both had hacks that were unsuccessful, but they nonetheless, in all cases, they were still able to break through the network temporarily and trying to seek information. And of course, the more concerning one, Germany had viruses that affected fuel rod system. So it actually monitors the state of the fuel rods. So this is going to come up a little bit later, but this is one of the things I'll say I was partially responsible for. I used to work with the Nuclear Regulatory Commission, and one of the first things we did was say, hey, take the plant operations and completely separate it from the rest of the networks. Not something that's easy to do in every field, but it's basically the opposite of what you saw at the water. So all of the information at a nuclear power plant is unidirectional. It comes from the plant out. Any information or data or software, you have to sneaker net into the plant. That's the only way to get it in there. So we'll see kind of the difference here. Just so you know, this is a very quick thing. I won't go into everything, but how a nuclear power plant operates. This is particular as a pressure water reactor. You have the radiation side here. This is the reactor vessel. That cooks stuff. That ends up not touching, but actually heating up the water in the turbine, which produces the power. And then, of course, that ends up coming back here, and you end up cooling it. Just so everyone knows, those big, giant towers that you always see and associate with nuclear, the reactor is not in that building. In fact, the reactor has nothing to do with that. And if you blew it up, it wouldn't really affect the plant. But so, and this, just so you know, is a spent fuel pool. So when a nuclear power plant, after the fuel has been used, they put it in a pool like this, and it sits there and it cools off for a few years. So it takes a few years to get cool enough before they can put it in concrete. Just so you know, that water, this isn't a great picture, but it's the clearest water you'll ever see in your life. There's nothing more clear than that water. Most places even make it. They take pure hydrogen and oxygen and actually make water just to put into that. So the chemistry is very important. They don't want anything to rust in there. They don't want to add any kind of other elements to it. So they keep that monitored pretty closely. So let's see a difference. This on the left-hand side is an organization associated with the water and part of the protections. And on the right is the NRC and NEI of some of those protections. If you look at the top there, they're expected to have an intrusion detection prevention system, which apparently they didn't. They were supposed to have a SIM so that they could log everything. Obviously, they would have known from where the attack came from if they had actually done that. And then down here, they're supposed to have multi-factor authentication, which clearly the 4-digit passcode, which is actually most likely just disabled, didn't do. So first off the bat, they didn't meet those requirements. But then let's compare it to the right side. On the right-hand side, you'll see on the nuclear side, they require data diodes and air gaps. Make it so it's very difficult to remotely control anything. You pretty much have to be on site in order for that to happen. And that the only data goes from higher to lower levels through basically a unidirectional device. So that's a data diode. So I'm pointing that out as a difference that you can make pretty drastic differences by the philosophy on how to defend these things versus just assuming it's case. So we'll hit another field. This one is, I find pretty interesting, is welding. So some of those are more direct. We went over, these incidents, and it's kind of like taking it down. Can you do something bad to the power plant, or can you shut it down, or something like that? Same with the water. But what you're seeing is a trend, which is, hey, you could do something that has an effect, not necessarily just on the operations of the plant, but could actually affect the consumers. So let's take this right here, which is, there's different types of known error types. You can improperly mix gases. You can have turbulence when you're doing the welds. You can have errors in joints. And so some of this stuff has real issues. If you look at some examples, Subaru recalled thousands of cars in 2019, and all of them were destroyed. And that was just due to them not knowing what was wrong with part of their frame. You had another one here where natural gas killed 8 and injured another 50. And so what's the basic threat I'm getting at here? We'll show this on another slide, but you can reprogram this to actually inject air into welds. And so what happens and what makes that difficult, I won't go over all that, but what makes that difficult is that the only way you can detect these air bubbles in welds is with X-ray machine. So the first thing is say, oh, well, you know, the cyber attack would be, oh, they break in and they just stop it from doing welds. But a much worse type of attack is to get it to intentionally, say 1 out of every 100 or so, you know, car frames, intentionally inject air into the welds. And what will happen is the weld, which is usually one of the strongest parts, actually becomes brittle and will just break. So you could be driving down the road and suddenly your car frame just falls apart. The interesting thing about doing that is if you only did it to 1 out of, say, every 100 of cars, they only tend to check one weld on one part of the frame, one every couple thousand vehicles. So the likelihood of them catching it would be very, very slim. Of course, the only way to resolve that would be to recall all of them. So that could be a very expensive hack that really didn't take anything out and would be hard to determine what caused it. So now we're going into food. So I'm not sure how many people know what this is. Anybody know what this is? It's a hopper. So it's often used to mix and measure quantities of things, chemicals, flour, whatever you kind of need to put into different things like food, right? So some of these examples are, you know, you can tell that thing to put too much into it, right? So you have a particular type of chemical and you can put too much into that. You could tell it to not mix it properly. And so when you put it in there, you could end up with a clump of really bad stuff with a clump of harmless stuff, all kind of put in there at the same time. So has this stuff happen? Yeah, not by a cyber attack, but you have like pet food recalls, where some of these chemicals, they literally use an eyedropper to put into there, and sometimes, you know, some of the food recalls for the dogs were just them misreading the instructions, and they put the wrong amount in there, and it ended up making a whole bunch of dogs sick. So the same kind of thing can happen. And as I'll show you here in a little bit, it's often in manufacturing, you have a system that controls almost all of it. And so usually you have a system, a control system, and in many cases, that's also the order system. They actually put an order in. It determines the chemical and makeup of the stuff to mix, and then it actually goes through the whole assembly line all the way till it ends up in packaging. And what will happen here is instructions fly up on the screen. Sometimes you have a worker, and it says to put in 3 bags of this and 1 bag of that. And they do what the computer screen tells them. If we change that and told them to put 3 bags of the other stuff instead and 1 bag of the other one, then you end up with the wrong ratio. And that can end up with a problem. So you end up here, and all that's controlled by basically one central computer system. Some of those, just so you know, are actually here in the United States, but the orders come in from all over the world. So they actually go in, get processed, and come right over there to the factory to be made. So another thing is similar to that is vaccines. So now you're talking about medical stuff. So some examples here. Bioinformatics, stabilizers. There's all kinds of things that go into making vaccines to make sure that they're safe. Temperature, as we all learn, remember some of the early COVID vaccines were very sensitive to temperature. And in fact, there was a person, again, not a cyber attack, but an individual that was upset that actually intentionally took all the vaccines out of the refrigerator, let them all warm up, and then put them back in right before they used it to intentionally harm people. And that was, I'm not sure everybody caught that, but that was on the news quite a while ago. So let's see. So on all these things, you can, adjust the stabilizers, you can affect temperature, like I said, and you can also cause delays. Most of those, from the manufacturing time to when it actually had to be in a person's arm, was in some cases down to just a couple days. If you just mix it up and tell it to go to the wrong place, next thing you know, all that vaccine's bad. So this is just going into details on that. I'm not going to go all through it, but it explains how the actual monitoring of the temperature and most of these things is all digital. For good reason. You want it to be fairly accurate, but it also means it's a potential attack vector. So what does this mean? It means we're all doomed, right? Well, I don't think it's quite that bad. So the first thing is the fear, uncertainty, doubt everyone hears, and that's FUD, and then likelihood, which is a chance that something will happen, or the probability. And I'm defining all this so I could talk about it. Risk, which is the possibility of loss or injury, and consequence, which is something produced by a cause or necessarily following from a set of conditions. So risk is, hey, I could get in a car accident. Consequence is I could die from that car accident. So it's important to understand those differences. And I want to talk about this because this is a big area where it's a little bit different between information technology and operational technology. The information technology, you'll hear, just like you tell everybody on a regular basis, about risk, and most of the time that's financial. One of the things you hear a lot of places is don't spend more money on an asset, defending an asset than it's worth. But that gets a little harder, as you see, when we're talking about consequence. So over here, just so you know, this is real quick, there's a whole bunch of ones where both chemistry and different types of attacks can affect major parts of critical infrastructure. So fear, uncertainty, and doubt. So when you first tell people about some of these things, it's the sky is falling, and that doesn't do anyone any good either because you become just kind of immune to it. So the big thing is understanding what the difference is between the FUD and the actual stuff. And so when you hear things like the end of the world is coming, or it's all going to chaos, or don't trust anything, then the problem is you're probably in the FUD space. The same kind of thing here. One cyber attack's going to just completely destroy the plan. Well, those things are probably not very true, but you can have some definite effects of some of the things I was talking about. So I want to kind of clarify that I don't think that a historic and theoretical attacks are FUD. It's a big difference. So when you go over there and you're looking at with both eyes open and say, this is a potential thing that can problem, that allows you to move forward and determine what you're going to do with it. Saying there's nothing we can do and everything's the end of the world's coming is truly kind of FUD. So one's responsible and I don't think the other one is. So, does anybody know what the likelihood is to die by a shark bite? How much? Handful of people. It's 1 in almost 4 million. So pretty low risk on that, right? But yet there are tons and tons of people who are pretty scared about getting bit by a shark. But then you got the likelihood of dying by a car accident. What do you think that is? 1 in 84. So, you know, if you jump a little quick, this is not an accurate way of looking at it, but, you know, you ought to be a little more scared about driving into the beach than going into the beach to get bit by a shark, right? But on the other hand, we're pretty good at understanding you really don't want to get bit by the shark. Forget about the risk factor. In all cases, you don't want to be the one, right? You don't want to be the one that dies in a car accident. You don't want to be the one that gets bit by the shark. So another example of that is this. What's the likelihood of death in an earthquake? 12 million, huh? It's actually more likely than the sharks, at 1 in 160,000, and death by opioids. Pretty close, 1 in 98. So out of all these things so far, you know, hey, opioids is a real problem on that. But let's look a little bit more carefully at some of this. So I don't know how many people have heard this before. This is not by me. This has been repeated a couple times, but it's called the Tale of Two Earthquakes. And this is really interesting, at least to me. In January 12th of 2010, Haiti was hit by an earthquake. And interestingly enough, just 1 month later, Chile was hit by an earthquake. And when you look at this, you start comparing them. The Chile earthquake had a magnitude of 8.8, which I'm not sure if everyone knows, but you know, an earthquake magnitude is exponential. So going up by a point doesn't mean it's just a little bit worse. It's astronomically worse. So you can look at a couple different things between all this. In Haiti, 230,000 people died. A slightly worse earthquake in Chile had about 550 deaths. So a giant difference between the scale of the number of injured, the number who died. But one thing you can kind of pick out there is what the GDP is, right? You know, they spent, the GDP was a lot more per person in Chile, right? They have more money, basically. So one of the other things is, you see, Chile had a long history of them. They've had a bunch of earthquakes. So, you know, that's a big thing, is why is one much better than the other? Well, Chile had all these things. They had standardized building codes. They learned from past experiences. They conducted earthquake drills. And like this says, this quote here, the difference between being in an earthquake and being a disaster is a level of preparation, right? We all know this from cybersecurity. We got to prepare, and that's what it is. So if you wait until after it happens, it can be a disaster. If you're prepared for it before, you know, it may not be such a big disaster. So that gets to some of the discussion here. I'm going to talk about risk for a little bit. So in the Webster Dictionary, risk is a possibility of loss or injury. Then you get to NIST. NIST says, you know, the risk is a function of likelihood of a given threat sources exercising a particular potential vulnerability and the resulting impact of that adverse event on the organization. Then you find another NIST entrance, which is got a very different one. And in fact, if you do it again, NIST has 32 different definitions of what risk is. So take your pick. So now I want to talk about consequence. So again, you got Webster, something produced by a cause or necessarily following from a set of conditions. Well, when it comes down to it, NIST says, effect change or non-change usually associated with an event or condition or with the system and usually allowed, facilitated, caused, prevented, changed, or contributed to by the event, condition, or system. Can anyone explain that to me? That's kind of what I had. I looked at it and said, I've read that a million times and go like, I don't think consequence is that hard to understand. And they made a paragraph that I still to this day can't completely translate for. By the way, I know lots of people at NIST, and this is not knocking them in any way. It's very difficult to write all this stuff. But I want to make another example of these things. What is the likelihood that glass will break when hit with a feather, a brick, or an axe pick? Right? Same thing here. What is the risk posed by hitting a glass with a feather, a brick, or an axe pick? And finally, what is the consequence posed by hitting a glass with a feather, a brick, or an axe pick? Right? So one is the risk, and of course I skipped over the likelihood. There's, that's related to. But, if you're going over here, the consequence of breaking a glass is, it's relatively minor, so you broke the glass. But in a different context, breaking that glass might have some pretty serious consequences. It's a glass walkway, you probably don't want that to break. So that consequence has a dramatic effect on what you're going to do. You're going to spend a lot more money probably making sure that glass doesn't break than you are the previous picture. And that's why I think it's important to not lose sight of that. You can get caught up in understanding the risk and saying, well, the risk is really low, but if the consequence is very high, it's something we still have to consider. I think that's probably jumping ahead there. So the first thing is people are generally terrible at assessing risk. People will look at one thing like the shark bite and say, oh my God, there's no way I'm going in there. And assume that that's really bad, but then they could look at something else like driving to the beach and not think twice about it. Same thing here. People are much better at estimating consequence. If you're standing on the ledge right here, then if if there's a 12-story building, the consequence is probably pretty bad. If I fall off of here, maybe not so much. More information does not necessarily yield better decision making. So sometimes you can get all this information and it can actually start to cloud your judgment. You can start to, so a lot of times what we do, especially in cybersecurity, is say, if we just had enough information, then we would be able to defend everything better or to be able to make a decision about what to do better. But it's important to have the right information, not just an abundance of information. And then this is one here. This is my personal opinion, of course, but a lot of frameworks emphasize risk, which is something that we're bad at, and de-emphasize consequences, which is something that we're good at. And I just want us to start thinking about that, especially as you move farther away from information security into real life cyber physical type security. And this is just saying, no, I'm not against NIST or any other framework like that. I think they're perfectly fine. Just understand what the limitations are. And that's all I got here. I kept it short for you. Does anybody have any questions or comments? But what does it do? Yeah. That is an excellent point, and it is a real problem. The first thing to understand is that most of these environments, at least at the moment, it is very, very difficult to do updates, even if they were completely connected. The main problem is when you get into something that's operational, there's going to be a lot of concern about doing the updates that could impact the operations. And so what you see is that they are very slow to respond to those. And, you know, we're trying to now get them so that they're willing to do updates even once a year. I mean, they've had systems out there that have been there 20, 30 years and never received a patch. That's just the sad truth of it. That's why we advocated very much, like you said, to disconnect a lot of these things as the start of this, was because you know, if you could get on a network like that, it's kind of a lot of home free for a hacker to cause a lot of havoc with that. The good and bad news is that like I said, a lot of those systems do have analog also. And so some of those things, you know, I believe a lot in physics. So if there's an alarm that, you know, basically goes off due to something having to do with physics, and it's not really a decision made by something digital, then that's something you can kind of rely on. I am a believer in that for especially safety systems. When it comes to safety, important stuff to kind of segment that off. In terms of what we could do, there's two things. One is, they've had both. They've had a lot of people in critical infrastructure where they were told perpetually that the sky's fallen and that they're one hack away from everything getting destroyed. No one's going to buy that. You know, they're tired of kind of hearing that. Unfortunately, that swung the pendulum the other way, which is you do have a lot of denial. They think that, you know, that's just impossible to do anything, especially if it's air-gapped, which is just not the truth. The ones that are truly air-gapped, you can't even see what's going on those networks. So if something's there, it could have been there for a decade and you wouldn't know. But excellent point.